of the platform. The Davis method, to whom is not familiarized with it, is a very powerful tool used to obtain a complete static analysis of robotic mechanisms, and it's based on the Kirchhoff laws, the graph theory, the screw theory, and some linear algebra. Briefly, the Davis method needs to have a representation of the mechanism by using graphs. So first of all, we need to obtain the structural graph of the mechanism, and then we can expand this graph into an action graph containing all the internal forces and efforts of the mechanism. Once you obtain this action graph, you can apply on it the Kirchhoff laws, and you can obtain several cuts on the graph, obtaining a matricial representation of it. So here we have a generic representation of the action matrix, representing all the cuts of the action matrix, where you can identify easily the primary and the secondary variables of the system. Or you can understand that variables as being the input and outputs variables of the system. So then when you have this action matrix, you can incorporate the screws on it, substituting the elements with value equal to 1. And then by algebraic manipulation, you can solve the final static model. This is the starting point in order to obtain a range capability model. Formally, talking about range capability, this phenomena can be defined basically as the maximum range that can be applied or sustained by a manipulator in all the directions for a given pulse and based on the limits of their actuators. So in this case, you can, for example, have a maximum force or a maximum moment in a specified direction. The range capability in robotics is of fundamental importance because they can be useful, for example, to find the better configuration for a manipulator to perform a given task. So here, for example, you can see a planar manipulator trying to drill an object, and you can see that the force in this direction in red could be, for example, minor than this force in this other direction in green. You also can find the better operation point for a manipulator to perform a given task. So here, for example, you have a complete map of the forces or the range capability of a mechanical system, and you can identify, for example, several regions where the force is higher than in other ones. Then the range capability could be useful also to improve the efficiency of the manipulator, to reduce the cost and better understand the behaviors of the manipulator. So in order to better understand how the range capability was obtained in this study, we solved this problem via optimization. So the aim of this optimization problem was to maximize the force applied at the end effector of the manipulator, this force called Fm, and is directed by a theta angle, while the moment at the end effector of the manipulator is imposed as a constant. So as you can see, this angle theta can vary, and you can obtain finally, evaluating all the possible direction of the angle, a polar representation that we can call, in this case, as the force capability map. This is actually not a real force capability map, but it's just in order to represent the idea. So in order to solve this problem of the force capability, we used a differential evolution algorithm. Specifically, we used the Sturm-Price algorithm that basically is a very simple population-based stochastic function minimizer and very powerful at the same time, in order to solve this objective function, where basically tries to minimize the error between the obtained and desired angle, the obtained and desired moment, and at the same time we maximize the magnitude of the force plus an element representing the penalization of the objective function. Sorry. Just in order to exemplify, we can take several platforms that actually are not redundant, hyper redundant platforms, and we can see that for each of these mechanism or robots, you can have a polar representation for the force capability. These figures are well known in the literature. I am calling them just in order to exemplify that the fact that you can have a polar representation of the force capability of the system. So then that you have this force capability map for a constant moment, you can, for example, start changing the imposed moment, allowing you to obtain, for example, a three-dimensional representation that we can call as the polytope of the mechanism, the force capability polytope. And each of these polar representations is saw as a slice of this three-dimensional representation, while the moment is represented on the z-axis. So in order to summarize, for this manipulator, for example, 3RR parallel manipulator, we can obtain for this central position this polar representation and their corresponding polytope. So jumping into the hyper-redundant manipulators, we need to conceptualize some important ideas. The first is that a kinematic chain is considered redundantly actuated when its number of actuators exceed the minimum number of required to perform a specific task. Also, when its number of actuations exceed the minimum required for performing a task, it can be considered as a hyper-redundant actuation chain. And finally, in two-dimensional space, it will say that a robot is not redundant if it has up to 3 actuators, is redundant if it has more than 3 actuators, and is hyper-redundant if it has a number greater than 6. In this case, we studied the phenomena in 3 manipulators containing 7, 8, and 9 actuators at the base of the system. So this is a 7RRR planar manipulator, and we can see so that applying the proposed method, we can obtain this polar representation and its corresponding polytope, that is a three-dimensional representation of all the forces and moments on the end effector. The same idea can be applied for a manipulator with 8 actuations, for this 8RRR planar manipulator. So we here have the polar representation and its corresponding polytope. And finally, the same idea for a manipulator with 9 actuators. Well, the conclusion, this paper presented a method to obtain the force capability polytope in different planar hyper-redundant parallel manipulators. The method requires the optimization of the torque in the actuated joint for the manipulator by imposition of a moment at the end effector of the manipulator. The force capability polytopes obtained here are composed by the superposition of several force capability polygons and depend on several parameters as the manipulator's kinematic position, orientation, working mode, and redundancies. This study may be extended in various ways. Manipulators with different degrees of freedom, kinematic chains, and including dynamic behavior may be studied. The study of different range capability indices may be considered in future research. Also, a close mathematical solution for the problem can be proposed. Well, thank you very much for your attention. If you have any question, you can write to me to this email, or if you want, you can talk in these few minutes we have now.
Thank you, Leonardo. Nice
Thank you very much.
Hi, Leonardo. I have a question. This is Juan Antonio Carretero from UNB. I must say that this is interesting work. It is quite close to some work that was done a number of years ago, if not almost identical in my opinion. So essentially, you do some sort of ray tracing using a differential evolution algorithm to find the boundaries of that range capability workspace, considering the maximum capabilities of each one of your actuators. So this has it has now been solved. I think within the last 8 or 10 years has been actually solved without having to do the optimization. It has been solved in a closed form, in that based on the fact that what you're actually doing is taking a parallelepiped in the joint space. So you're taking the force capabilities of each one of those actuators and their maximum and minima, so the maxima in both extremes, and they don't need to be symmetrical. However, the polytope that you have called from the joint space and then map it using your Jacobian of your hyper-redundant manipulator, it is indeed a linear mapping, right? So you have a linear space, which happens to be a parallelepiped or a hyperparallelepiped in the joint space. When you do the linear mapping in the Cartesian space, which is now your the space that you're representing this, you call it a polytope. It is more specifically, it's actually a zonotope because it's centrosymmetrical. You can actually do it in closed form, mostly because the linear mapping of a linear object, the end result is also a linear object in hyperspace. Of course, in your case, it's just planar. Well, three-dimensional because you're considering projections. Am I correct in that part?
Yes, you are absolutely right. But first of all, and before to make some comments, I would like to say to you that it's an honor to me to be in the same session with you, because I know very well your work together with the work made with Professor Knockleby. You both developed several approaches in order to solve this problem. And you are absolutely right in your contribution about the problem has closed form solutions. Actually, we have proposed several closed form solutions for the problem. We based our work initially on your scaling factor method. That was a very, very beautiful solution for the problem. And we proposed several improvements for the methods, because originally the method used some optimization in order to obtain the values for the variation of the moment. We obtained a closed form model, avoiding the use of the optimization. So to me, it's a very big honor to be talking with you about it. In the behavior of the system, you are absolutely right. There is a linear behavior between the actuators of the manipulator and the force capability. So it's possible to obtain. In this case, we decided to use optimization because we need some numerical results, because these numerical results will feed another research where we are going to try to train a neural network. So we needed some numerical results, and that was I don't know, it was
But if you have the zonotope, so if you do the linear mapping of your polyhedral space that you have from your joint capabilities, which is a hyperparallelepiped,
yes,
right? Because it's lined with the axis.
yes,
You do
you
the
are right.
mapping, the linear mapping using your Jacobian matrix and obtain a zonotope. The end result is the vertices of the zonotope. So you do have numerical values for the coordinates of all the vertices on the zonotope in the Cartesian space.
Yes,
So
for the vertices
couldn't
is
you feed your
relatively easy.
neural network without avoiding? I know that when we moved from the work that we did, Scott and Venus, we did about 10, 12 years ago, we moved on to doing it in closed form. I may not be exaggerating by saying we probably save 99.9% of the computational time because it's closed form. You just need to, if it's a hyperparallelepiped, you just take the vertices of that hyperparallelepiped. In our case, we had, I think we tried up to 12 dimensions. You can compute very easily the vertices of a 12-dimensional parallelepiped, and you only map those points through the Jacobian matrix, obtain a cloud of points, and again, using the fact that the linear mapping of a linear space is also a linear space, a zonotope, once again, then only you need to use the convex hull of those points, and it's finite. And the convex hull is a very simple, it's a very well-determined problem that has, its computational time is almost trivial, I would say,
Yes,
compared to everything
you
else that you may be doing. So your neural network is probably because you're doing optimization, you're doing control. So that's that part, whatever you're going to use it for, that's great. But if you're looking for computational efficiency, maybe you should be looking elsewhere, in my opinion.
yeah, you are absolutely right, Professor Carretero. Thank you very much for your
I,
comments.
I have a comment here. Well, I do agree with Carretero about this issue that using the zonotope and the polytope it's direct and it's a bit more efficient, maybe more, because we improve about a lot the situation, because some part of the solution was closed form. But there is an issue that we intend to apply this to those parts that were neglected by the zonotope polytope approach, because one of the, for instance, this is an ongoing research. One issue that we want is like for designing a robot, sometimes some joints or some links have a strong wrench, so they can break, because you can use like a very feeble leg. And using the zonotope and the polytope, we ignore completely those parts. You go directly to the end effector. But using the approach as an optimization problem is just adding one constraint, and we can derive everything just adding constraints. So we can add extra constraints, and then we can optimize. This is what Leonardo did. It's just a ground basis for replicating most of your results, but including a way to add like the force, the torques, and the limitations and the strength of materials inside the parts that are neglected by going directly to the end effector. That's one point of a counterpoint.
Thank you very much, Professor Daniel.
Okay, my last comment. First, let's keep the discussion short. Otherwise, the last people in the program, they will not have time to present their paper. At this point, I want just to say a comment that probably in this work, you should have emphasized your experience in attaching the problem from numerical point of view. In the sense, probably you should have given some more details on the efficiency or accuracy what you got with your numerical procedure, maybe even with a comparison with what Juan Antonio said about the glossy form solution. That is a suggestion for your future development. We can discuss, but we don't have time. Okay, thank you.
Thank you very much, Professor Marco. So, any other comment? Well, we are short of time, so next, Bruno Rocha presentation was canceled. So next, Irakose Vivens is here.
Marco will present.
I'm here,
Okay, Professor Marco.
on his behalf. Okay, I think you see my screen
Yes, we are.
or not?
Yes, we are.
Okay. Oh, okay. Also, my connection is not so good, but I hope it will be enough. So this is a student paper from Irakose Vivens. He is student of the curriculum, International Curriculum at University Tor Vergata on Engineering Science. And he did his bachelor thesis on this historical technical analysis of harmonic drive gear design. The aim of this work was to understand how and the motivation for the development of harmonic drive, and also to let the student to understand the technical peculiarities and the advantage that make this gear transmission successful in many areas. So this is just what I said, that the complexity of the problem was one of the issue that needed a lot of experienced people attaching the problem, and the solution was in fact this design. Well, the paper is centered on the this US guy who patented the design of harmonic drive in 1957. But we also discovered that in the same period, and this is mentioned also in the paper, there were some other similar studies in Russia. So just to say that the problem of looking for solving the disadvantage of traditional transmissions that you see listed there in terms of large space and problem in maintenance, the high cost, a small range of application. You have to think that in that period, in the 50s, the machinery were evolving very rapidly to very automatic system with high performance. And we start to see also the first robots that needed some special compact lightweight design for the joint transmissions. So back to this, to the figure of this inventor, the student searched about on his life, and what is discovered that he was not really a researcher, but it was much more a practitioner and a professional working on manufacturing companies for many years. And he came out with the problem of improving the solution that he had on his hand for some machines. The other things that the search on his peculiar experience during his profession is that he based his expertise in this specific field mainly on practical experience since his youthness, and also he got let's say not an easy career and this is what he also simulated him in order to search some other new, I can say, line for his profession, and this made it possible to develop his idea in that achievement for that time was not immediately recognized. Indeed, a lot of people expert in gear design, even they didn't understand even the concept of harmonic drive. Here you see on figure 2 the patent, the last, well, the successful patent version for the harmonic drive that was submitted in 1959. Here is the concept of the harmonic drive. As I told you, he developed in several patents. The most important one is the patent in 1959. And here you have the main part of the patent explaining the functioning of the harmonic drive, how nowadays most of us will recognize the structure with the 3 main components, with the key element in the flexible geared ring, internal ring, and also all the explanation in the quite long text of explanation, and also, as you may see in the second figure B, how the engagement of the teeth was progressing by deformation of the flexible ring against the rigid ring with internal gear shape, that made the concept of the harmonic drive that give the possibility to have a transmission ratio of very high values. You may know that now the harmonic drive can reach also a ratio 1 to 500. At that time, he could reach 1 to 100, which was much more that any gear train, even a epicycloidal solution could achieve with some small reduced compact design. So after this patent discussion, the harmonic drive was started to be produced quite recently after the last patent, but as you see, it took more than 5 years from the concept that was announced by Walton in 1955 to the first market component in 1960. Here is the main concept that now we know as produced in all the harmonic drive, and we teach in our course when we have to explain the functionality of this device. You have the 3 components. Flexible spline is that component that can be flexible in the sense that he can be engaged with the circular spline, which is rigid, and the peculiarity is that the circular spline and the flex spline, they have a number of teeth that can be differentiated from 2 to 3 teeth. Then you have the wave generator that is connected with a flexible spline in such a way that it's possible to transmit the motion either from the circular spline to the wave generator or vice versa. So this is just to say that the functionality, as I mentioned, has a unique property, high reduction ratio, lightweight, and compact assembly. Nowadays, I may say that the flexible spline is made not only of plastic material, but also of very flexible metallic part. And this is in order to increase the life or the fatigue durability of the gear, the transmission, because in this motion, the flexible spline is as is a peculiar functioning in having an elliptical shape that change over one round during the transmission. And also the other things compared with similar, I mean, competing gearbox with much more element is the simple construction that is summarized in fact by the three components that I just outlined. Well, in order to say that the success is that now this harmonic drive design is applied mainly in robot solution, because they can keep very compact the transmission inside even the joint design. And this is an example that we have reported to stress the success of the main peculiarity we just addressed. There should be an animation here of the functioning that Irakoke made by himself in order to better explain and to extract the main mechanical characteristic of the transmission that he summarized also in this in his kinematic modeling in order to derive this peculiarity and to find out the kinematic behavior of the system. Here is okay, it's modeling, dynamic modeling for a height application in which they use the motor, the electric motor. These are the design he considered for robotic application in order to understand even the robustness from mechanical point of view, considering practical design that are available from the market. And he analyzed this aspect by looking at stress analysis with finite element analysis, in which he could check the efficiency of the mechanical structure, as is reported in the plot in figure 7 and figure 11, related to the stress, the level of stress within the flexible spline and the wave generator, and also the life of the system by using the two measure of stress evaluation and von Mises stress analysis. He could find the values that are quite well below the capability of the material that he assumed to be built this component basically this was considering iron, steel, and some flexible aluminum alloy for the flexible spline. In these two plots summarize the value of this measure as function of the critical nodes in the mesh that he built. And in conclusion, so I hope we stay in the time, this is just a student study in order to understand who and why developed this new solution. So in order to give an historical background and also to let the student to understand how an invention can be produced with individual efforts, individual interest, individual experience, and also he made this work has given him the possibility to fully understand the peculiarity of the design of harmonic drive, and he applied its capabilities in order to characterize the design. And in these two figures, once again, he wants to stress the peculiarity of the design and the three component on the left design from the patent, the Walton patent, with the peculiar engagement of the gears, and also the explanation of this functioning by considering a linear engagement of the system, like for linear version of the harmonic drive. Well, that's all from his work, and I think I may say that he got a good experience, a good satisfaction of this work, and I hope this is also useful for the student listening in this symposium, and also for researcher, because we can still discover some new questions, new aspect that need to be better explained, better investigated, and perhaps even improved also in this well-known and well-exploited gear design. Thank you very much.
Thank you very much, Professor Marco. So is there any question for Professor Marco? Any question?
I have a question. Could I?
Yeah, please. Yeah.
Just a simple question. In your finite element analysis, are you using contact analysis between different parts?
Yes.
Yeah.
Yeah.
Okay. I see here. Yeah. So, sorry.
Yeah. You see here. I didn't activate the pointer, but here you can see. Yes.
Yeah.
And well, actually, from the video screen, you cannot appreciate the number, but the color helps to understand how much is the level of stress.
Yeah, and the stress is higher in the rotor than in the teeth, in the contact tooth.
Yeah, apparently yes, because in this design, he checked, he analyzed an existing design, so he got he get the parameters from the technical sheet of a commercialized harmonic drive, and yes, that is quite curious. That seeing the main stress is the wave generator. Well, yeah, it can be reasonable, because if you look at the concept of the design, we may expect that the most critical part is the flexible spline. And in fact, most of the attention in the design is addressed to the flexible spline. So such that in the result, in the real operation, flexible spline looks not to have a critical issue, although, as I mentioned before, he suffered fatigue because he is cyclically deformed from in its elliptical shape during the revolution of the flex spline.
Yeah, I guess there is some friction and sliding between.
Yeah, that was another problem for his simulation, to identify and to assume proper friction in the contacts. So actually, as I mentioned, this is a student, but he simulate a reasonable friction at the contact of the teeth.
Yeah, that differs in this harmonic drive. That differs from the classical gear. Normally, classical gear do not have sliding at the contact point. Do you have a sliding at the contact point here? Yeah.
Yeah, because you have the flexible spline that is engaged during a motion. Let me see here. Here you see in the bottom there is an adjustment of the engagement, and during this, I'm indicating the bottom of the first figure in this conclusion. So you have a certain friction during the engagement, and also during the engagement itself, because the engagement is moving. The flexible spline that has 2 or 3 teeth less than the rigid gear has a movement against between the two teeth. Yeah, this is one of the limit of this analysis, because for sure we should need to investigate, and actually this is what I was mentioned before. This can be an aspect to improve the design and efficiency of harmonic drive, to study better what happened at this contact in terms of friction, loss of energy, because there is a heating either in the flexible spline and in the gears of the rigid ring.
Yeah, and just a final comment. How are the tooth profiles selected in this kind of drives? Because the theory is not the same as in standard gears. It's completely different. No?
Well, in the original design by Walton, the gears are the original profile that you can find in gears. To my knowledge, I think that they use the traditional profile.
Okay.
The involute profile. I don't think they have different profile.
Okay. Thank you. Thank you very much.
Thank you very much. Any other comments or questions? Well, okay. If there is not any other,
I can get out of the condivision. Okay. I get out from the condivision. So okay. Thank you very much.
Thank you, Professor Marcos. So then next presentation belongs to the dynamic analysis session. It will be made by Federico Cavalieri. So Federico Cavalieri is from Argentina. So are you here, Federico?
Yes, yes. You can see my presentation?
Yes.
Okay.
Okay.
Sorry. Okay, thank you. Hi, everyone. And this work, the title of this work is Modeling of Spherical Rigid Bodies with Sliding Friction Contact Effects. And this work was prepared by members of 2 groups. The first one is CIMEC. It is on the National University of Littoral and National Council of Scientific and Technical Research, CONICET, both institutions of Argentina. And the second institute is the LTAS, which depends on Department of Aerospace and Mechanical Engineering of University of Liège from Belgium. So as introduction, in this talk, I will present 2 topics. The first one is the multi-body system, and the second one is the non-smooth dynamics. As you know, a multi-body system are mechanical systems composed of elements as springs, actuators, spring dampers, and etc. And the second topic is the non-smooth dynamic, and it is produced when jumps on displacements, velocities, or acceleration occurs in a very short period of time as a consequence of impacts. For example, here you have 2 real-world applications of multi-body systems subjected to non-smooth dynamics. For example, in the ball bearing as consequence of the gap. For example, for the wear effect, you have impact between the ball and the casing, or So it, as consequence, generates display acceleration of displacements, or in other more complex systems, as the gearbox of this wind turbine, the gap between the shear box, the teeth of the shear box generate impacts and then generate acceleration, which propagates for the rest component of the structures. So the objective of this work is present a novel implicit model to consider contact between a rigid spherical body and a planar rigid surface, taking into account first impact and sliding friction, and second arbitrary movement of the spherical bodies in 3D. We use an implicit contact algorithm which fulfills exactly bilateral and unilateral constraints at position and velocity levels. So the general form of the equation of motion at velocity level is given by this, for this set of equations.
Federico, sorry, your audio is not working well. Could you please repeat?
Now you can listen it.
Yes, now it's okay.
Now it's okay. Sorry.
Yes, now it's okay.
Sorry. So again, the equation of motion at velocity levels is given by the set of equations where here we have the definition of the velocity. The second equation is the momentum balance, where m is the mass of the system, which can depend of the coordinate vector q. dv is the measure of the velocity. Gq is the constraint gradient. Di is the measure of the impulse, and F is the vector which collect external damping and internal forces, for example, and dt is the Lebesgue measure. This equation is we have the other equation to represent the bilateral constraint at etc. And the third and the fourth equation is to represent the impact between bodies. Here we have the equation of the Newton impact law. In this equation, we have a phenomenological coefficient En, which is the restitution coefficient in the normal direction. And here we have a second equation for the impact to consider friction in the simulation. And we need also another phenomenological coefficient, Et, which is the restitution coefficient for the tangential direction. This equation, remarked in yellow color, and name it the Newton impact law. So in the framework of time integration algorithms, we can be classified in two big groups. The first one are the event driving scheme, where the time step is adapted, so the time step is variable. In general, efficient is the number of event of impact occurs. And in the second group, the event capturing time stepping, the time step is not adapted, so the time step is fixed. And the content constraint at velocity level are imposed by an impact law, for example, the Newton impact law. Here I show you. Or other laws, for example, the Poisson impact law. Other alternative of time stepping method is the non-smooth generalized alpha. It involves a high order approximation of the smooth terms and enforces exactly all constraints at position at velocity level, as we see later. It less numerical dissipation than Moreau-Jones scheme in flexible problems. and has been formalized and tested in frictionless and friction cases, as we see later in the numerical example in this presentation. And it poses minimal modifications in existing fine element of the library. So if we use this scheme, we don't need to modify previous element of the our code. So in this slide is the time stepping scheme. I don't want to spend too much time in the explanation of this integrator because we can be found literature. Here I give you the reference just to, I would like to present the main idea of this time stepping. The idea is to isolate the impact contribution from the smooth contributions. So the impact are integrated with first order accuracy, and the smooth contribution can be integrated with higher order scheme, for example, the generalized alpha scheme. So we have here three sub-problems. The first one is solved, as we tell you, with a generalized alpha scheme, and then appear two other problems for the position contribution and the velocity contribution. This algorithm can also interpreted as an active set method when the three sub-problems are solved at each time step by using a semi-smooth Newton method. So the element that I present here is a sphere in contact with the plane. The picture is in 2D, but the equation is for a general 3D moment. Here we have the sphere with the node A in the center of mass. We have the inertial frame, and the position of this node is given by the vector xa, in this case xa, and it is in the previous time step, and xan+1 is the vector or the position of the node A in the current time step. Then the plane is fixed, and we have a node B referenced with this vector, and we have here a frame n normal to the plane, and two tangential vectors to the plane, T2 and T1, which go out from the scheme. So the generalized coordinate is given by the vector Q, where in the first component we have the incremental rotation vector. Then if we take the derivative of Q with respect of time, we have the velocity vector. So for the constraint at position level, we have the restriction. This is the gap vector, which is formed by three components, Gn, Gt1, and Gt2. Gn represents the minimal distance of the surface of the sphere with respect to the plane. So if Gn is equal to 0, the sphere is in contact with the plane. In other case, the sphere is not in contact. Gt1 or Gt2 is this tangential displacement or tangential incremental displacement. So for example, here we have T2 multiplied by xn n+1 minus xan. So this difference represents this arc length, this distance, sorry. I show it here in blue color. And the incremental rotation multiplied by the radius of the sphere represent the arc length of the sphere when the is. So this length is equal to the arc length of the sphere. So the sphere is in rolling movement or in sticking. In other case, the sphere is in sliding because this distance on the plane is different to the arc length of on the sphere. For the velocity contribution, we have to derive this gap vector with respect to the time and include the Newton impact law. We have the restitution coefficient in the normal and in tangential direction, and the inequalities constraints for the contact is the same at position level. For represent the frictional problem, we selected the friction column law. This law is formed two big set of equations. The first one corresponds to the normal contact, and the second set of equations correspond to the frictional contact problem. So here, for example, nu n represents a Lagrange multiplier in the normal direction. Nu t is the tangential Lagrange multipliers, and mu is the friction coefficient. So the regularization of this frictional contact condition is solved by an augmented Lagrangian approach, as Allard and Cournier proposed in quasi-static problems. So we take this idea and we include this augmented Lagrangian to position level, taking into account the friction problem. Similarly, the frictional contact problem at velocity level is given by this set of equations. Here, lambda capital N represents the normal impulse, and in the tangential direction. Similarly, as before, the regularization of this frictional contact condition is solved by the augmented Lagrangian approach of Allard and Cournier. But the difference with respect to the position level is that here we use the Newton impact law for the normal and for the tangential movement. So the virtual variation of this Lagrange multiplier at velocity level gives the internal force vector and position and velocity level with the different contact status depending on the movement of the sphere. As we use a semi-smooth Newton, we need to linearize these force vectors. So we obtain here the Hessian matrix at position and velocity level for the different contact status. Until here, the theory, and here I will show you some numerical examples. The first one is very simple. We have a ball which is in contact with this plane. The ball has an initial velocity 0.2 meters by meter by second, zero angular velocity. Initially, the ball slides and then enter in input rolling, and we can verify with analytical solution the numerical results. But this set of equation is easy to demonstrate this equation. This is the time when the sphere enters to roll, and this is the angular velocity when the spheres enter to roll too. Just to show you, I present here the solver parameters and the numbers of iteration at smooth, at position, at velocity levels, the maximum number of iterations, and the average of the iteration. Here I show you a video where the first slide, then entering rolling, and finally impact with this wall. In all cases, friction is considered. Proposed by Felipe Marquez, Paulo Flores et al. The authors presented this mechanism with all rigid bodies, and we reproduce the solution of these authors, and we added a second case, including the flexibility of the connecting rod. So in this mechanism, we have here and a hinge in this at this point, a hinge here, so representing the bilateral constraints. The roller is in contact with the ground, and we have here friction given by this friction coefficient, and then is applied to the crank an initial angular velocity of 4 radian per second, and in the roller we applied 8 radian per second. Here is the solver parameter and the maximum and average iteration of the on the smooth and position and velocity levels. Here we have the numerical solution. In red, we have the acceleration, the angular acceleration of the roller. We study the angular acceleration of this point as Felipe Marquez and Paulo Flores proposed. So in red, we have the angular acceleration for the rigid case, and in blue, we have the case when the connecting rod is flexible, so you can see this oscillation as consequence of the flexibility. Then here in this picture, it's interesting to see that the roller rebounds in 2 opportunities, and the constraint
Federico, sorry, I think your audio is falling again. Are you here?
Yes.
I think Federico has lost his connection.
Okay.
Federico? What do you do, Martin?
Yes, we will do a break. He will
Yeah.
share the next session, so he can show us the final result after a break. We can take a break up until 13:45. Okay.
Thank you very
Let's
much
take a
for
break,
all.
and then I will continue with changing the session of dynamic analysis with Federico Cavalieri if he is available. If not, we will continue the another talk. Thank you, everybody, and we will do a break to have lunch until I will publish now until 13:45.
Okay. Thank you.
Thank you.
You can hear me?
No, yes, but
Ahora
recently
sí,
not.
pero
I'm sorry, the connection breakdown. Sorry, I don't know what happened, but my internet break. Sorry. So I will try to return to the
Federico,
presentation.
we will do a.
Yes. Yes, Martín.
Anuncia una pausa hasta las 1:45, así que puedes mostrar el resultado a las 1:45.
Okay. So.
University of Campinas. On here are the topics of this presentation. So in the last decades, planetary geosets have been widely used in industrial applications and are currently considered as one of the most important types of transmission systems due to their compactness, high overall efficiency, great transmission ratio, and also a considerable load capacity, which allows this kind of transmission system to be applied to many heavy duty applications, as the one studied in this work. And however, it is important to mention that the cyclic gears require accurate continuous inspection and maintenance, as they are usually subject to tough operating conditions. And also the failure of such crucial system means a significant economic losses, since the repair demands an appreciable amount of time, resources, and also technology. So in the literature, published studies have been shown that multi-body dynamics approach is a very good, alternative to investigate guiative contact forces, evaluate kinematic characteristics, identify vibration of transmission mechanisms, and also analyze via meshing frequencies and compare those data with experimental tests. Although much work has been accomplished for dynamic characteristics, on dynamic investigation of fixed axis gear and also epicyclic gears, there is still few available research data about multi-body dynamics of multi-stage planetary gear trains. And in this sense, this paper aims to fulfill this research gap. And therefore, the main purpose of this study is to analyze the dynamic meshing forces of a two-stage planetary gear train, which is commonly used on variable speed hydrodynamic power transmissions used in oil and gas field. And the idea is to develop a multi-body dynamic model and using co-simulation between Adams and Simulink computational environment. The influence of the inertia of those elements of this machine are going to be discussed and analyzed with regards to the kinematic and dynamic response. So regarding the simulation model, the machine is characterized by a hydrodynamic power transmission equipped with an 11 megawatt electric motor, which acts as the main input power of the system. The electric motor, according to the power split principle, split the input power between the torque converters pump and the main shaft of this machine. The hydrodynamic power transmission, actually the hydrodynamic torque converters pump, which is in red, transmits the power to the turbine, which is coupled to the sun gear of the first planetary, PGT1. It is also important to highlight that the carrier of the first planetary is fixed, and the ring gear of the first planetary is connected to the carrier of the second planetary. This connection represents the superimposing shaft, which is one of the elements analyzed in this study. Also, the PGT1 carrier is fixed, as I told you before, and the remaining power of the main shaft is connected to the ring gear of the second planetary. And finally, the output shaft is connected to the gear of the second planetary, which drives the desired machine, as we can see in green. So once the main objective of this study is to analyze the influence of the element's inertia of this machine, a model was developed in Adams machinery toolbox, and then control on input variables was controlled according to the call simulation of Simulink computational environment. And this simulation tool is very important because it allows the implementation of variable inputs that can be controlled according to the dynamic response of the Adams plant. So we have the dynamic response over here in the turbine torque, and the torque delivered by the main shaft, the output torque, and the kinematic responses of the elements of this machine. So regarding the contact force calculation, this contact force for the multi-body dynamic model is calculated according to an impulse function method, which is prescribed by two main components. The first component is the elastic component, which is a non-linear spring characteristic. And the second one is the damping force component, which is expressed as a function of the contact collision velocity, x dot. And also we have the contact stiffness, which was obtained based on the Hertzian elastic contact theory, where the pair of the contact gears can be estimated as cylindrical bodies. So it's a estimation for this kind of estimation. And also we have the damping coefficient, which is around 0.121% for this study, was used around 0.1% of the contact and stiffness. And also we have the regarding the friction parameters over here. So for the study cases, in order to investigate the effects of the inertia and the negative contact forces, 5 case scenarios were analyzed, and the first one is the baseline configuration with no modified inertias. The second one and the third one are the modification of the main input shaft inertia by an increase of 50% and a decrease of 50% respectively. In fourth and fifth cases, which are the modifications of the superimposing shaft inertias, as we can see in this table. So for the simulation results, the 5 study cases were discussed. The first analysis is based on the contact forces between the Mejía teeth of the planet and the ring of the second planetary, as we can see over here. And these figures illustrate the first 5 seconds of the simulation. As it can be observed that the maximum forces of the contact forces are placed around the first 2 seconds of the simulation during the motorway startup, and after this it occurs on a decrease of these forces for the first case and the third cases, which are the baseline configuration in the case with the reduction of the main shaft inertia. For the second case, on the other hand, as we can see, there is a smoother variation in the applied forces. In this case, there is a reduction of approximately 18.5% of the applied forces, of the contact forces, meshing forces, with respect to the baseline configuration. And this is primarily due to the fact that an increase of the main shaft inertia results in a reduction of the rotation acceleration. So we have a decrease of the contact forces. And for the third case, as we can see, which features less main input shaft inertia, there is a greater rotation acceleration, which affects directly the backlash effects. And that causes an increase of around 34.1% of the meshing forces when compared to the baseline configuration, which is in yellow. So in the third case in cyan. And a similar characteristic can also be noticed in the meshing force profile for the contact of the sun planet of the second planetary. So it's very similar, as we can see in comparing to the planetary in contact. So besides the main shaft inertia, another major component of this analyzed machine is the superimposing shaft element, and it was also analyzed. But as we can see, unlike the main shaft element, the variation in the superimposing shaft inertia did not represent an expressive change in the Mejía teeth contact. And this is mainly due to the fact that the input shaft receives most of the power if you compare it to the superimposing shaft case. So the main input shaft has actually a greater influence on the Mejía teeth contact forces for this case. And we can also see the kinematic characteristics, the speed curves. So for the first and third cases, we can see a greater variation. In the fourth case and fifth case, it is only a slight variation when compared to the baseline configuration. We can also see that the second case and the third case affects directly the turbine speed. And we can also see that the deceleration of the turbine for the baseline configuration, for example, around 2.7 seconds, it happens because of the viscous friction force generated by the hydrodynamic torque converter as the main shaft accelerates, and it starts to converge to a specific point around 15 seconds. The same happens over here, as we can see, the second case, which is it delays a little bit the acceleration because there is an increase of the main shaft inertia. And the opposite case happens for the third case, as we can see. So in this work, the effect of the inertia on variation of elements of a multi-stage planetary gear train on the gear contact forces were investigated. A multi-body dynamic model was developed using co-simulation between atoms and simulated computational environment. And based on the simulation results, we can see that we can conclude that the main shaft inertia had the most significant influence on the contact forces when compared to the superimposing shaft case. And also we can state that the multi-body dynamic co-simulation found to be a very useful tool to investigate dynamic behavior of planetary gearboxes and prevent such transmissions from eventual failures, for example. And this work was supported by the following organizations: University of Campinas, Petrobras, the Italian Brazilian company, LabSim, Laboratory of Integrated Systems, and CNPq and CAPES. Thank you very much for your attention.
Thank you, Samuel. Some question for Samuel?
All right.
May I ask one question?
Yes,
I didn't follow completely because why do you have oscillations in forces? What is the origin of these oscillations? Because
these oscillations,
yeah.
So it's basically because of the model startup, because we put an input speed on, for this case, which is around 1,800, I'm sorry, RPM for the input speed, which is a constant speed for this case. So based on this call simulation, we have the model in the Adams machinery toolbox, and we put a target speed to achieve during this process. And this variation is supposed to be because of the contact, because there is a backlash effect between the teeth contacts, and that's why it happens.
Because what I mean, if the gears were perfect, you would not have these kind of oscillations, don't you?
Yeah, I agree with you.
Okay,
yeah.
Okay. So the origin is backlash and some initial excitation. That's your explanation. Okay.
Exactly. Yeah. Based on this parameters, because there is actually a calculation which is a non-linear spring characteristic for this case. So we have a lot of parameters regarding the simulation. We can set those parameters according to the Adams simulation, and we can also control those input and output variables according to the call simulation. I don't know if this answers your question, but it's something like this, right?
Yeah, okay. Thank you very much.
Right. Yeah, perfect. You're welcome.
Any other question? So thanks again, Samuel. Thank you very much.
Right.
Next presentation will be projected by YouTube. Mohamed is here.
Yes, I'm here. I'm here.
Okay, I will present your YouTube video.
Okay, please.
And then you will be able to answer the question. Just let me know if it's, you can hear the.
Hello, everyone. My name is Mohammed Shahada Saleh. I am PhD candidate at Harbin Institute of Technology, Harbin, China. I'm happy today to talk about the research article titled Efficient Modeling Procedure of Novel Grading Device Using a Multi-Body System Approach. Our paper proposed a multi-body system procedure for a novel aperture grating device, which considered as a complex rigid flexible system. The multi-body model is constructed based on assumption due to the grating movement. This movement can be usefully utilized in different types of application like laser generation and optical communication. Recently, researches and development have made progress in the area of optimization, modeling, simulation, and design of creating the device, including kinematics and dynamic analysis. Server method used for the modeling of creating a device based on finite element analysis. Finite element analysis can be considered more suitable for modeling elastic bodies subjected to small deformation behavior, while the grating device show definite rigid body motion. The multi-body system dynamic becomes the most economical Vienna in product design and optimization of complex mechanical system, and it can be used for the systems that show definite rotational as well as small deformation. The multi-body model in this paper is used to estimate acceleration and Lagrange multiplier. The Lagrange multipliers can be used to compute the dynamic reaction forces, which can be used in the design process and the optimization process. The numerical modulation are developed using MATLAB symbolic tool books with very efficient computational procedure. Kinematics of grating device motion. The grating device can be easily defined as a typical parallel mechanism. This mechanism includes 2 translation joints and 1 spherical joint, and can make 5 degrees of freedom, move along the x-axis, move along the z-axis, and rotate about 3 axes with theta phi epsilon. The dynamic equation of motion that defines the motion of the rigid body and the flexible body can be derived using augmented formulation in this form, where MRR is the mass matrices of rigid body, MFF is the mass matrices of flexible body, CQ is the Jacobian matrices which can be derived from the constraint equation, the partial derivative of constraint equation by generalized coordinate. QR and QF is the external applied forces acting on the rigid and the flexible body, respectively. QD is the quadratic velocity vector. We solve this equation to obtain the acceleration and the Lagrange multipliers. To drive the equation of motion, the constraint equation, we first define point with the point in the grating mass. It can be defined with respect to local frame and defined with respect to global frame with this equation, where A is the transformation matrices function in generalized coordinate. The system can be analyzed as follow. We have about 14 bodies is joint to each other by different type of joints. As example, the fixed base is joined to a ground with fixed joint. The generalized coordinate for every body can be defined 3 for translation and 3 for orientation. We have 14 bodies, so we have more 100 generalized coordinate, 84 generalized coordinate. The equation, the constraint equation of rigid or fixed joint between fixed base and the ground can be read as this equation: 3 to constrain the translation and 3 to constrain the rotational. Also, the prismatic or translation joint can be defined similar to fixed joint by defining points in the action of translation and define this point with respect to first body and define this point with respect to second body, and derive the constraint equation for prismatic joint. Also, the constraint equation of spherical joint can be obtained similarly by defining this point B. It can be defined with respect to body 3 and defined with respect to body 4. And as we mentioned before, we can define the constraint equation for spherical joint. As we can see, we have 3 constraint equations because the spherical joint can constrain the motion in 3 degree XYZ, but it can allow the joint to rotate about 3 axes. The floating frame of reference formulation can be used to derive the flexible the constraint equation for flexible the connection between flexible body and grating mass, similar to a rigid body. After we solving the equation of motion between acceleration vector can be integrated to determine the coordinate and velocity for the system, and the Lagrange multipliers can be used to determine the general reaction forces acting in every body, and this equation we can multiply the Jacobian matrices with Lagrange multipliers. We obtain the translation reaction force and the reaction moment or torque, and these reaction forces used for establishing the design process. Based on the multi-body model formulation in the previous section, the grating system model is created using MATLAB symbolic toolbox in the following steps. At first, we built 3D model of the grating device in SolidWorks CAD software. Then the system is fully analyzed to define bodies and joint type. The equation of motion items are the derived function on generalized coordinate. Solving the equation of motion, obtaining the system configuration and reaction forces. From the dynamic result, the design mechanical structure for grating detailing device can be optimized. Numerical simulation. The mathematical model of a small scale grating device is created. Is constructing using the multi-body approach using MATLAB symbolic toolbox. The initial parameter can be defined in this table, the masses and the inertia of the system. The external applied force coming due to piezoelectric actuator. It's about 4,700 Newton. And the integrator, the Adams-Basha force integrator method are used in the integrator process because it's very it's suitable for system equations that have rigid and flexible body with a small deformation problem. After we solve the equation of motion and integrate the acceleration, we obtain the system movement. The point P in mass in the mass grating mass, the point P movement can be computed from the mathematical model in this table. The displacement of grating mass is about 3.5 millimeter. The orientation of the maximum orientation of the grating mass can reach 2.5 micro rad. The reaction forces can be computed easily. Can be computed also the reaction force and the reaction torque. Also, the flexible body configuration or displacement can be computed, and also the reaction moment acting on the flexible body can be computed and used to define or the flexible body. As a conclusion, we built a mathematical model of grating device system using multi-body system approach. The type of computational models is important in all phases of analysis, design, and control of such systems. Based on the simulation work, with the multi-body model, the optimal design of the grating device can be established. In our going and future work, the multi-body model will be verified with real system and used for full system identification of the grating device to compute and model the parameter like joint fraction and design optimization of the grating device. We tend to finish the real system. It's very complex. Thank you for your listening.
Thank you. Some question for Mohamed. I will preserve here the presentation. Is there any question?
I have a question.
Rogelio?
I can see in the last slide that the device is probably under construction. I would like to know which kind of sensors are you using to sense the position?
Are you there, Mohamed?
Yeah, I'm here. It's called the displacement sensor. Displacement sensor. It's very, very, very expensive. We bought it from Germany with his controller. He can measure the displacement.
These are cell phones. These are cell phones.
This is Bezo. This is Bezo. This is Bezo.
Okay. You can annotate here.
Sensor is in the lift. This sensor.
Okay. Displacement sensor.
Displacement sensor. Yeah.
Probably they are they capacitive sensors?
Yeah. Ultrasonic. Ultrasonic.
Ultrasonic.
No contact. There is no contact. He measured with ultrasonic because the movement of the grating mass, because it's using laser generation, it's micro and nano. So he can measure very, very little distance.
Thank you.
Any other question? Thank you very much, Mohamed.
You are so welcome.
Thank you. Meanwhile, Fabrizio Santisioli here.
Hi, I'm here. Yes. Can I share the screen?
Yes. Fabrizio will present the work by Águila Chávez de Carvalho. It is called Shear Mesh Stiffness and Damping Co-Simulation.
Okay. Thank you for the introduction, Professor Martin. Can you see the screen, please?
Perfect.
Okay, thank you. So I'm presenting this work here, gear mesh stiffness and damping co-simulation. We are a group of 6 authors, and I'd like to tell you something about the scenario we were facing when we were starting to write this paper. We had the proposal to study a complex machine, and we had part of this machine implemented in Adams, the dynamic part of this machine implemented in Adams, and another part, the control of this machine implemented in Simulink. Then later we were dealing with the gear systems of this complex machine, and we thought we can use Adams RED tools for gearing, or sorry, I think it's going automatically forward. Sorry. Then we thought, should we use the RED tools of Adams to model the gears, or should we try to model by ourselves? Then we decided to model by ourselves because we could have better understanding about this part of the machines. And we could model the gears based on the literature. So we started to use MATLAB Simulink and diagram blocks to model not only our control parts, but also our transmission parts. Okay. We decided to use very simple elementary model of gearing, the one proposed by Young and Son. It's more or less old for our cutting edge articles. It's from 1985, but it's good for first implementation. It has just simplified stiffness and damping between the gear teeths. So we decided to start from this model. In our group, we have other people modeling high detailed gears, but we started from a simple implementation. In this implementation, we consider the Hutchesian theory and Coulomb friction to analyze the stiffness and the damping. So, as I said before, we have part of our machine implemented in Adams and another part, the control parts, in Adams Simulink, and it becomes a very powerful tool to join both together. We can have all the control tools from MATLAB very powerful, and we can have another very powerful dynamic modulation from Adams. Then we can decide which part will be in both environments, and then they can get matched together. So this is part of the modeling of gears. We can see in the screen the kinematic relations between two gears, the gear 1 and gear 2. Further, we can see that gear 1 is placed in a O1 center and gear 2 is placed in a O2 center. Both have inertia, J1 and J2, and both can be submitted to torques T1 and T2. For gear 1, counterclockwise is the positive direction, and for gear 2, clockwise is the positive direction for angular displacement and for torques. We can see also that we have backlash here between teeth. We can assume this backlash as B, the distance along the common normal line between the teeth of the first gear and the second gear, if they are aligned, as we can see in this picture here. So based on these parameters, we can set a relative displacement between both gears, as we can see in equation 2. It's related with the radius of each gear and the angular displacement. And this relative displacement in gears is not actually, it is limited by the teeth. And we can say that if the displacement is bigger than the backlash, we can say that gear 1 is pushing gear 2. If the relative displacement is smaller than minus the size of the backlash, gear 2 is pushing gear 1. And among these limits, we can say that there is no touch between the gears. So the dynamic equations of the gear pair changes depending on these conditions. Okay, so in each gear we can have the torque in the shaft plus the damping and the stiffness between the gear contact. From the literature, we got the stiffness factor and the damping factor, and we could model our system. We translated all these equations here to block diagrams, and we connected the block diagrams in Simulink to an Adams plant. From this Adams plant, we have the communication between both software. Okay, and we use a smaller gear as the driver one and a larger gear as the driven one. So from very briefly, we can say that the kinematic and the positions from Adams, they are translated to MATLAB Simulink. From MATLAB Simulink, we calculate the forces of contact, and these forces are they feedback the Adams model, and everything goes on in a loop. We have three scenarios. The first scenario is based on initial velocity for gear 1. The second scenario is based on driver torque on gear 1 and resistance torque in the gear 2. And the third scenario is based on an initial speed of gear 1 and the sinusoidal torque also for this gear in high frequency. So let's see some results. Here we have the relative tangential displacement between the gears in the case of just an initial speed in gear 1. We can see in the second graph the angular displacement of both gears, and in the last graph we can see the angular velocities of both gears. So in the first one, in the relative displacement along the common normal line, we can see that the teeth are hitting each other. It causes the inversion of the movement, closing the clearance between teeth in a positive and a negative directions. And it's reflected by the angular displacement of the gears. We can see how gear 1 has tilting angular displacement, and gear 2 has a bigger radial and also bigger inertia, so it's clearer for gear 2. And we can see also this phenomenon in terms of angular velocities. Here is the second case when we have just driver torque in gear 1 and a resistive torque in gear 2. We can see how they start to touch each other, and this graph of relative displacement, it fades to an steady condition, goes to an steady condition when a tooth is touching the other one almost without kicking the driven one. Okay, it's tend to regular touch, constant touch because of the damping of the model. And then the angular displacement, and we can see also angular acceleration, both in angular displacement and angular velocities. Finally, we have in the third case, initial speed of gear 1 together with high frequency sinusoidal torque. And we can see the displacement between teeth very noisy because of this high frequency torque. But we can see also transfer of movement between the gears due to the initial condition of gear 1. We can say as a conclusion that we could implement model that we chose for us for a specific component of the machine, we can say that we can do it in MATLAB and communicate and transfer the information to atoms as it's necessary for us and necessary for the model. And we could verify that the results were very similar to the literature. Then it's the essential parts of our paper. I'd like to thank to our university, our laboratory, and our sponsor. And thank you. I am open for the questions.
Thank you, Fabio. Thank you very much. So is there any question for Fabio? I have one. This work is connected with the presentation by Samuel?
Yes, we share the same space, the same rooms, and the same projects. Yes, it's connected to the work from Samuel, but Samuel didn't use this model for his work, but they are in the same context.
So you can simulate shear trains with this.
Yes, we can make something more complex and join other blocks, other block diagrams, and make something bigger for sure.
Okay, thank you.
Thank you.
I have a question.
Yes.
Yes, Juan Carlos Jauregui from the University of Querétaro in Mexico. I have a question, Fabio. A very nice presentation and nice way of solving the problem. But my question goes regarding, can you explain the advantages of doing all this combination of softwares compared to the traditional modeling with the transmission error and the backlash as a single function? What will be the advantage of doing all this? Is more accurate, or what is the advantage?
Yes. Actually, sometimes when we are building a model in Adams, for example, we can choose between make our own routines for the modeling of specific parts, or we can choose to use something already built in Adams. For example, Adams gives us the possibility to choose between 3 kinds of gears, of spur gears, 3 kinds of modulations of spur gears. But sometimes we feel like missing information about what this model from Adams really does. So if it's possible, we can also choose to make our own routines. For example, in this case, we made in another software, but we can also make this inside Adams and build our own specific routines for something that's more critical. As our group started a project in which we studied the gears, and it was in the very beginning, when we wrote this paper, we decided to take very simple kind of gear modeling from the literature and investigate if it would be possible to implement in Adams and also in Simulink to see what would be the difficulties, what would be the benefits. And what I can say is the following. If we have a co-simulation, sometimes we pay the price for a longer processing time. But if we have a co-simulation, we also can have more information about the real modeling. not the one someone did in MSC, for example, the one we made by ourselves. Of course, it depends on the scope of the project. If it's a really critical issue to deal, for a general approach, okay, it's better to use the modeling specific from atoms. But if you are studying gears, I would recommend you to have a better knowledge of the gearing model. And that's the reason we decided to investigate further how to implement a gear model in atoms. I don't know if I could answer your question.
Yes, thank you very much. Great.
Thank you for the question. I think we have another question from
just a comment. There are classical publications in which, for instance, for gear trends, they are computing the vibration frequencies of the system and these kind of things. It would be important to verify your model to see how you match these results. If you want, I can send you some papers.
Oh, yes, I would like to receive
they are
this
classical, yeah.
Sorry, I couldn't understand.
But there are a lot of authors which model these kind of things, so as to, it would be nice to position your work with respect to theirs.
Yes, thank you. We opened this possibility to implement really, as you said, more complex gear modeling. So I would welcome if you, I would be pleased if you could send some further information, and I'll let my email here in the chat. Okay.
Okay.
Thank you very much, Alberto.
Say to you.
Oh, thank you, Fabio.
Okay.
So, in order to not be too late ending the sessions, we will jump the break and we will continue with the next block of presentations. The next section is prototypes and experimental validations. And the first work will be presented by Alexander Leano. The title of the work is Design of Handling and Extension Tool for Inspection and Maintenance of the Current Steam Generators. Alexander, are you ready? Alexander is from Argentina, from Centro Atómico Bariloche, the National Commission of Atomic Energy. Nuclear energy. Okay.
Okay. No, I couldn't find the audio is activated when I start to share the it.
Yes. Go on.
Give me. Okay, I don't have we pass with this. Okay, sorry for inconvenience. Okay. Hello, everybody. My name is Alexander Leano. I'm going to present the design of handling of an extension tool for inspect and maintenance of current steam generators. This work was developed as a part of the robotic division in a current project in a National Commission on Atomic Energy in Bariloche. One of the driving motivation for robotic research and use of robotic to avoid exposure to hazardous environment of the human. No? The nuclear industry is filled with potential use for robotic and automation because there are hazardous environment involved. A very restrictive policy regarding safety and the radiation doses operator can take. And because, as any other industry, it research to reduce cost. an important increase the use of the robots in nuclear and after Fukushima accident. Here we can, I don't know when, that's the point. Here you can watch some robots used there. Because there is not simply other way to inspect, stabilize, and start the contamination and the commission inside the reactor building. Other countries, for example, US or UK, also have an important program to use robotic in nuclear, mainly for the commission and the contamination task in their legacy nuclear facilities. Here we can watch on one of them. Robotic underwater robots and drone, for example, or use a robot to manipulate contaminated devices. Okay, but what we talked before is in general in a life cycle in a plant. There are proposed different systems, but here in our project, in the current project, we propose the use of robotics from the design. And this current project is different to others reactor vessel because it have a steam generator inside the pressure vessel. Here, this is the yellow, and we have the red part is the enter to the steam generator. The current project is an Argentinian concept of modular reactor. It has an innovative safety measure as integral part of this idea. The use of robotic and automation is being included from the design to different tasks. One example is the development of robotic system for inspection and maintenance of the steam generators. The inspection of the steam generator tubes is performed every time the reactor is stopped for refilling, approximately once a year. Here we can watch the distribution, 12 identical steam generator with 52 tubes each that are placed equally distant from each other. Among the inspection tasks, one of the main tasks is to inspect these tubes here in order to check their integrity. The proposed system that includes the use of commercial available robotic manipulator, a set of custom design tools, and a rail transportation system here to take the robot and each tool to the room, to each workstation inside the reactor shielding room. As we can see, the industrial robot has a limited range that guarantees the absence of collision with any element inside the shielding area. Okay. The robotic cell interact with the Planar with the objective to inspect the tubes here. To reach this tube, you must enter through the opening to the steam generator, removing the flange cover. This is the one to reach 6, where it is the steam generator or a connection to the steam generator tubes. To do this, we develop a task list required here. The picture depicts a sample for the diagram of this task, and the list in the middle implies to reach the plate 6, and this list to do this is take the pressure drop devices here and inspect the wells too here inside, inspect the tubes. Look the tube is necessary and insert pressure drop device here. This list in the middle, the limit range of the robots. For the limited range of the robot, we can reach this here, and for that we need an tool that extend this range of the robot. It will result in a need to design this tool to increase the reach. This tool might be able to couple other tools or devices, which with the ones that perform each one of these tasks. As we can see, this extension tool, we can call this EMA for the Spanish acronym. It's needed for this pilot task, basically for the tasks that work inside the Planar. Hence, insertion tools was designed at the same time as the other special tool for each task. Two important tools, or the most restrictive tools for the EMA design was the PEG distractor pressure drop devices, a PEG for the Spanish acronym and Spanish pronunciation, tube extender here. This is a concept that replies the distribution of the tube's plate holes, but in the position of the flange. Both of them was designed in parallel with EMA. Okay. When selecting which mechanism type to use the increased range robots, the following criterion was taken in account: the simplicity of mechanism, the reduction to a minimum extra system needed, the electric conductor, signal, cylinder, motors, standard and reliable components, control variable reduced to a single axis in the space. It is in the way to reduce the extra system needed. One of the common movement needed for all of these tools to be manipulated with the EMA is a linear movement. For that, one design criteria was a linear movement. Okay, hence a commercial available linear compound model was selected as a principal component here because it had a linear movement. We designed this prototype here. To put all this part was a relationship with the geometry and the masses distribution. To interact with the robots and tools, we use an industrial pneumatic loop changer here in 3 and 4. And rest is the distractor. This is the main component. And other parts are component to adapt the tools to EMA interact. This design was iterative, included in a virtual environment simulation for testing a robot routine task. This simulation was used for the geometricals of different mechanical designs and trying to find possible interference in the final work environment and evaluation of different robot movement. We are going to show some of these in a simulation in the Delmian virtual environment in this section. For the design and manufacture of the tool was necessary to have a mechanism capable of simulate as closely as possible to the real environment. In particular, we use Delmian robotics software. Okay, wait. Sorry. Okay, now. Here we watch one of the first exercise we do. Here we can watch the task highlight before, in the list before. The robot take take the EMA, and now here talking the PEG. This to take the drop devices, and after this left the drop device, the pressure drop devices here in this tool trolley mockup. Here we can watch when take the extensor tube. Okay. Here we can see the mockup of the robotic cell we developed and manufactured it. Included the purchase of the commercial component and assembly of the part. Finally, the integration process, the EMA in the robotic cell. We can see here the robots, EMA, and a PEG. Here we can see here a tool trolley mockup is a rack to the tools. The extensor tube put in a plenum mockup. And unit control here behind. We can see here to the EMA manufactured with the part we talked before. Here I have a video to show the integration. All of them is in progress. We can see this in the video, the approach routine. Just with the enter. Oh, this was quickly. We can see here when we talk the extensor tube. Okay, this is an approach routine. This is all in a high velocity, but we can, as we can see, the approximation with the extensor tube, what is slowly, because there is a very restrictive in geometry with this, and we are doing this carefully in the beginning. Okay. In this work, analysis was developed. It determined the necessity of the tool to extend the range of the commercial robot. The design of the EMA was developed as well as an iterative simulation of the tool, its interaction with the robots, with other tools and the environment. And the EMA prototype were manufactured and tested successfully. In the complete integration of all of this tool is currently underway to achieve the validation of complete system validation in one-to-one mockup. Okay, here the dream team. Thank you very much.
Thank you very much, Alexander. Is there any question for Alexander? Juan Antonio. Please.
Yeah, thank you for the presentation. It's too bad that the videos are a bit choppy, but I think I could see the idea, the principle behind it. So I have a question in regards to the insertion. As you showed in that demonstration, you had the robot take a piece, which is a very long piece. You have an end effector that essentially has a prismatic joint on it. You twist, you turn around, and then either remove or insert an object onto a hole, I guess, right? So that's essentially what you're doing. So my question is, this object that you're inserting is fairly long, from based on the scale I can see is probably in the order of 1.5 to 2 meters, right?
Yeah. That's
okay,
something like that.
So what is the angular velocity? You're using a commercial robot. I think being orange with black parts, I think it must be a KUKA robot, either that or an ABB. But the angular resolution of those robots is not extremely high. It is not bad for a commercial robot, of course, but they're not extremely high end. And when you propagate that displacement over 1.5 meters, what sort of clearances, I didn't get that from the presentation, what sort of clearances do you have on the tubes as you're inserting them, so that as you propagate that error over 1.5 meters, you do not, you can still meet your tolerances?
Yeah, okay. First of all, sorry for the chopped video, because it was for the time. I was chopping the video to show it, but this is on YouTube. It's a video more explicative of this. Okay. The tolerance we are using now is for this video is more than 1 millimeter, but 1 millimeter is the tolerance we are using to this. It was more than millimeter now, because we are tested, and for that, and we manufacture this part, and for that we prefer something smaller, something smaller that we are going to use, and we are going to put now some extra parts and start to excuse me, here the second. and put extra part to close to this 1 millimeter of tolerance that we are going to use. You know, this tolerance is needed because we need to put or use these tubes to go to the plate in the end. Yeah, that is true that the propagators, the error in the end are going to be bigger than 1 millimeter, but in the, okay, if you can watch, give me a minute. Here in this part, we use some extra part to adapt, you know, to adapt to the tools. This part is to adapt to this tube extender here, and for that we took the tube extender from here, and the other part is guide with for this piece here, and for that is it is close to the robot connection or the robot coupling.
I can't really see what you're pointing, but I'm assuming that object number 6 there is what's guiding.
Yeah. This
Okay.
is what is guiding.
So, and whatever you're guiding doesn't have any deflections? I mean, over 1.5 meters, these are relatively slender rods, what you're inserting, isn't it?
Yeah, it's when okay, a ver, give me a second. No, this video, if you can put it here.
I think for the sake of time, maybe we can take this conversation offline.
Yeah.
Actually,
take this offline if you want, or ask me by the mail. The mail is no, okay. No, I can't put this part. No, okay, no, it's just is the part that is chopped. Here, this piece. Okay, here. Okay, we have an approximation routine to do this with the robot, and in one part, this is a point. This in English. This is a point to support this part, and when it left to guide, start to guide the plenum.
Okay. Thank you.
Okay. Thank you, Alexander. There is no more time for question. We will continue with the next presentation. Thank you very much, Alexander.
Thank you very much to you.
Okay. Next speaker is Anthony Gutarra, and we present the work hexapod walking mechanism based on the clan linkage for a 2 degree of freedom amphibious robot.
Yes, I'm going to share my screen. Okay, can you see my screen?
Yes, perfectly. Thank you.
Okay. Thanks for the presentation. Good afternoon, everyone. My name is Anthony Gutarra, and I'm going to present our paper, Hexapod Walking Mechanism Based on the Clan Linkage for a 2 degrees of Freedom Amphibious Robot. This is a brief summary of the content that I'm going to explain. We start with motivations. Interest in bioinspired morphologies lies in their best adjustment to the ecology and the behavior that it demands. However, much of them have limitation to operate in more than one environment, which has motivated to develop multi-environmental robots. Floyd proposed a water runner robot inspired on Brazilian lizard for its ability to run on water surface. This mechanism has 4 legs composed of 4-ball linkage, each one. Kim proposed a hexapod amphibious based on clan mechanism to achieve a path parallel to the water surface. So our paper is based on both studies and develop a mechanism. And in this paper, we present the kinematic analysis, the structure design, and the prototype building process of a clan mechanism for an amphibious robot. And second, analysis of the clan-based leg. And we start with verbal linkage analysis. A clan mechanism is composed of two verbal linkage. Therefore, the analysis of only one verbal linkage is made. The imaging show a standard verbal linkage, and this equation solve the angular position of θ3 and θ4, and the coordinates of the n effector of the verbal linkage, the interest point, call it P. These equations are based on the computationally efficient method proposed by Constant. So, considering this, we continue with a standard clan mechanism. Clan mechanism has 1 degree of freedom and is composed of 6 links. For each revolution of the clan, the n effector of the mechanism describes the trajectory shown in this figure. The position of the n effector relative to a mainframe in the initial point of the clan is calculated as a function of the 6 links, the angle of the bend links of the mechanism, and the cran angle. And this function is obtained by dividing the mechanism into 2 verbal linkages, as I mentioned before. So this is a standard clan mechanism. And we optimize that. For the optimization, the initial path, as we can see before here, is obtained in function of the initial value, V0, considering the standard clan mechanism. And the decided path is composed of 3 parts, showing this figure. The decided path is a triangle, as we can see here, represented by red lines, and the initial path is represented by blue lines. The desired trajectory is composed of 3 parts. The first part refers to a horizontal movement to achieve maximum drag effect of the legs of the mechanism in ground and water surface. The second part refers to a slope path that reduces the cycle time of the mechanism. And the third part refers to a vertical movement to reduce the negative drag force during the downstroke of the legs in water surface. Here is a brief diagram of the clan mechanism. Okay, we continue with optimization. The cost function, J, is the quadratic sum of the difference between the decided path, PT, that I explained before, and the current one, P. This is shown in this equation, where N is the number of path reference points, and V is the vector of variables to optimize. The vector includes the length of the links and the angles of some bend links. And the optimization also considers velocity, because each reference point is associated with an instant of time. The imposed constraint is in the range of minus plus 20% of the initial value, V0, which imposes the Grashof condition. The optimized vector B is obtained using a MATLAB function, fmincome, which is a gradient-based optimization method that requires the initial values that we use considering the standard clan mechanism. And the values shown here represent the optimized values of the mechanism. We continue with kinematic analysis of the optimized leg. The kinematic analysis has taken into account the optimized values of the mechanism, of the clan mechanism, and is considering only 1 cran revolution, as we can see here. For the velocity, we use forward finite difference per each axis, and the results are shown here. Third, the amphibious mechanism. The imagine shown here represent the proposed prototype for the mechanism. It has a dimension of 30 by 15 centimeters, and all the pieces are printed on 3D with PLA, and the mechanism consists of a mainframe and 6 legs. Each one of these is made up of a clan mechanism, and all the movements of the mechanism are controlled by 2 motors, motor A and motor B, and each one of these manipulates a 3-leg set, as we can see here, the B set and the A set. The components of the mechanism are DC motors, pulley transmission system, a mainframe, a styrofoam base, a clan mechanism for each leg, also a foot for each leg, a multiplier transmission gears. Exist two configurations for the displacement of the mechanism on different surface. For displacement on water, doesn't exist a phase difference between the angular position of the 6 ground, as we can see here in this image. This arrangement is proposed to achieve maximum drag effect of the mechanism in water surface, in water and ground and water surface, and it was experimentally determined. For displacement on water, on ground, we propose a tripod gate. In a tripod gate, a three-leg set forms a triangle, as we can see here, which center point is the summing point of forces acting on the legs, and when it points acts in the same horizontal line than the center of mass of the mechanism, torques doesn't appear in the roll direction of the robot. And this is the arrangement we can see here. Interaction force of the mechanism on water. A styrofoam base is used for having a buoyancy force. The styrofoam density is 50 kilograms per cubic meter, less than the water. So it covers the entire bottom surface of the mainframe with a thickness of 30 millimeters. The drag force generated by the interaction of the feet in the water follows the unidirectional displacement of the mechanism on water. And as we can see here, the buoyancy force acts over the styrofoam base and the drag force acting on each leg of the mechanism. For experiments, we made the analysis considering only one leg, only one clank mechanism, and not for all the robot, as we can see here. These are the results for the position of the end effector of a clank mechanism. The real shape obtained is represented with the black dots, and the simulated is represented by the blue lines. And in this case, the mean absolute error was from 17%. In the case of the velocities, also we can see the real shape obtained with black dots and the simulated with blue dots. In this case, we energize the motor to obtain 20 rad per second of velocity in the crank of the mechanism. And as we can see in general, the magnitudes of the simulate values are smaller than the simulate. The real are smaller than the simulate, and this is because we don't consider negative effects such as friction or no uniformity in the mechanism. In the margin show here, we can see a prototype. We can see the first prototype, and we use this prototype to prove the buoyancy force and the drag force acting on the mechanism and not in the displacement. Now we are working on the displacement of the mechanism, but these results are not part of this paper. So finally, we have some conclusions. First, the clank mechanism was used for the legs and was optimized to work on both surface, on water and ground. The proposed hexapod amphibian mechanism was designed, prototyped, and is experimentally able to move on water and ground surface. And the experimental results of the legs trajectory were satisfactory for a good displacement of the mechanism. And that is all. Thanks for the attention.
Thank you, Anthony. Very nice prototype. Very interesting. Is there any question? Anthony, who is the owner of this idea? Is there more works there? Could you go back to the reference there before this one?
Yes.
IEEE. Okay. Something similar?
Yes, we based it on both studies. First, Floyd, who designed, as I mentioned, a mechanism with 4 legs, and after Kim, and we use both works as inspiration to develop our mechanism, our mechanism. Yes.
Okay. Is there any other question? So thank you, Anthony.
Okay, thanks to
Let's
to
go
you.
to the next word by Giancarlo Ferreira de Oliveira.
I am here. You hear me?
Yes, perfectly. So
I will share my screen. Okay.
Giancarlo will present the word experimental analysis of the dynamics of an active cardanic joint with 3 degrees of freedom.
1 second. I'm working with 2 screens here. Let's see. Did you see my presentation?
Yes, perfectly.
Okay. Well, let's start. Hello, everyone. Good afternoon. It's nice to be here. My name is Jean Oliveira. This is my advisor, Professor Hans Weber. Today, I'd like to talk about the experimental analysis of the dynamic of an active, I will change here, active cardanic joint with 3 degrees of freedom. Okay. While I studied my doctorate, I did a book with my advisor, Professor Hans Weber, and I wrote 2 papers. This was my second paper. Okay. The book is available on the Amazon in Portuguese to graduate students. Okay. Advertising, sorry. Let's start. Well, the manipulator was designed and manufactured with only one active cardano joint, all right? And it was built with a loaded sensors on the base here. And this is the picture of the base of the loader sensor, okay? The inertial motion unit sensors on the end effector here, IMU here, and the 3 control boards, all right? The first here was designed to control the 3-step motor drives, 1 below of the bench, and other 2 in the joint, okay? And the last were designed to read the loader sensors here, the last board. Well, joints are basic components of robot manipulator, which have decisive influence in their performance. There are many types of joints. In my case, Cardan or universal joints, constant velocity joints, spherical joints, Thompson joints, and so on, okay? And the robot manipulators are applied in industrial, service, medicine, in aerospace, for example, in prosthetic applications, in surgical applications, industrial or services, for example, Cook manipulator here, in the aerospace, for example, asteroid lander and rock nozzles, and so on. The mechanism was designed using BIM methodology with the software Autodesk Inventor. It was manufactured and built with a commercial Cardan crosshead, motors, and reductions. The reduction assembly to the crosshead are the critical parts to design the mechanism. This is some pictures of my manufacturing process, okay? The stepper motor is model Neumann 17, and the reduction is by planetary gearbox of 1 to 720 rate, high reduction, right? Small and high reduction. Made in China, which is more affordable than gearbox and motors by Maxim, for example, made in Switzerland, okay? What does mean active joint? Active joints mean that input forces are inside the joints to control themselves. The joints can be run by wires and cables or directly driven by motors. The mechanical challenge of using motors directly at the rotational axis of the joint is the high torque necessary in some applications. The mechanical reduction demand concern because of the high torque and the small scale of all components. Mechanical reduction demand advanced materials make the joint expensive. In this picture, I broke the teeth of my gear, okay? let's start now the kinematic model. The first step is defining our frames. And in my experiment, I define 4 frames: frame F in green, frame Q in red, frame R in orange, and frame S in blue. Okay, and the angles between them, alpha, beta, and gamma. Then we have the transformation matrix by this expression. Okay, I use this notation for cos, sin, and tan. Right, simplify my notation. Then it's possible to calculate the angular velocity. Okay, as an antisymmetric matrix, we can calculate the body one here, the angular velocity of the body one, with this expression. The body 2 has angular velocity equal this expression, and body 3 has angular velocity equal this expression. Okay, this is omega 2. That is a web annotation, a notation of my advisor. All right. There is a phase shift in Cardan joint between the angular velocity of the shafts. Omega input is different of the omega output. All right, and that depends on the angle phi between the links here. We call this angle joint here. And then we have this expression of the omega output and omega input. Well, to develop the forward and inverse kinematic at the position at point P here, in frame F on board the F, right, be written by this expression. The vector R from G to P is equal the vector R from G to O plus vector R from O to P. But the last vector is on board S, then it's necessary to make a transformation here. And this way we can obtain the forward kinematics here, where we have the point here, P, X, Y, and Z, and the Cardan angles here with L1 here, length of the first link, L2, length of the second link. Well, the general solution of the inverse kinematic is not solved analytically. However, if alpha angle is known, then the beta and the gamma is given by this expression. Then it's possible to calculate, in this case, the inverse kinematic. Okay, then all the motion of the 3 bodies is learning using forward kinematics and inverse kinematics to solve the problem proposed with the manipulator robot. Let's start now the dynamic model. Okay, the dynamic model will have 3 bodies in motion. The body 1, 2, and 3 has a diagonal matrix. Okay, and the body 0 is stopped. Yes, is stopped. Only then the static balance is necessary, and we can obtain this 3 equation. For body 1, we can apply Newton-Euler law, the direct method, okay, at point O here. The body 1 here is in frame Q, and we can write this: the balance of the moment equal the derivative of the angular moment here, and we can use it. We need to use it too the parallel axis theorem or the Stan theorem. Okay, then we can obtain more 3 equations for body 1, and we can do same thing for body 2. We can apply the Newton-Euler law for body 2 and frame R in orange here, and we can obtain more 3 equations for body 2. And for body 3 in frame R in blue, apply again the Newton-Euler law. We can obtain more 3 equations. I created this constant to simplify my expression. Okay. Now put all equations together, it's possible to create the function phi here with the state vector, inertial matrix, and the geometry of the system. And we can obtain 6 reaction moments here, 6 reaction moments, and 3 torques. Okay, then this equations is my dynamical model. Well, let's play here and play here. Now we need to find the movement to compare the analytical results with the experimental results. Okay. This experiment, I defined the joint angle phi equal P per 6 radian here, angle between the links. Angular velocity of the angle of the joint plane, all right? Theta dot equal 0.4 radian per second. And output spin of my second link equal 1 radian per second. This way I can calculate the Cardan angles. This is a video of my experiment, okay? This is a simulate of my experiment, but without backlash. There is a big difference. And this is a simulation with backlash. But in this paper, I don't formulate the backlash, okay? I formulate that in my final work. Let's go on. Then we have the result of the kinematics. Yeah. And the first graph here, we have the beta and the gamma angle. And the second, we have the alpha dot, beta dot, and gamma dot. Okay. Analytical results, okay. And alpha double dot, beta double dot, and gamma double dot too. Okay. And angular velocity of the body 1, 2, and 3 in axis X, Y, and Z. This is my analytical results from the equations, the kinematics, and dynamic models. Okay. The reaction moments here, the 6 reaction moments here, and we have here 3 torques. Torque 1, the alpha motors, the beta motors, and the gamma motors. Okay. And now I need to compare my analytical results with my experimental results. I obtained the beta and the gamma here in dot line from the IMU, and I calculate the angle, and the continuum line is beta and the gamma is from analytical results, and we can see the difference. All right. From IMU2, it's possible to obtain the angular velocity of the body 3, and dot line is my experimental result, and continuum line is my analytical results. Okay. And now this graph is possible to see the F1 and F4, the point 1 and 4 of the load cell in dot line here. And continuum line again, my analytical results. I compare my analytical results with my experimental results, okay? Well, in conclusion, the objective of researching the kinematics and dynamics of an active cardanic joint was achieved. The results were within the expected margins of error for the experimental apparatus. And for the proposed movements, we obtained the positions, velocity, accelerations, in addition to the force and moments involved. The use of the motor reducer has become an interesting solution, since high reduction through planetary reduce can achieve the necessary torque for the movement. However, planetary gearbox becomes the main critical component to be analyzed. Also, research the torques involved in gear motors, including backlash and friction, becomes essential. And some improvements should be proposed in the future. For example, reduce the joint slack, readings of the IMU and load cells. Okay. This is my reference, and that's it. Thank you for your attention.
Thank you very much, Giancarlo. Any questions for Giancarlo?
Professor Weber is here.
Carlos Rodriguez, please.
Yeah, thank you. I saw in your graphs in the results that there is like, let's say, some non-smooth behavior of the analytical. Why can you explain that, like little ripples there in the analytical results?
In analytical result, what is this in the graph?
Yeah, exactly.
Is the impact of the backlash. Okay. Because I simulate the analytical result with backlash, but in the graph, but I don't show this formulation in the paper. Okay. And in this graph, we have the backlash formulation here, but I don't show this in the paper.
Any question? Any other? Juan Antonio?
Yes, so the backlash, did you, I didn't follow this part, I'm guessing. Did you artificially introduce backlash, or you wanted backlash so that you can model it and then showcase how good you are at modeling it? Because it seems to me that given the ratio, you had a 720 to 1 ratio, if I'm not mistaken. That was the gear ratio, isn't it?
Sorry, I don't understand. Please.
So you had a 720 to 1 ratio, gear ratio in your motor, if I'm not mistaken. Some very large ratio in the NEMA motors that you used, right?
Right.
Okay, so they originally came with a very large. Is the backlash coming from the motors, or is it coming from somewhere else? I'm just puzzled on how is it that it's so high?
I understand now. The backlash is from the reduce, right? The high reduce 12720, because this high reduction, I have a big backlash in my experiment. Maybe if I use the harmonic drive or other solution for reduce, I can minimize my backlash, right? But in this case, because this reduce maybe from China, but is the big reducer I found in the market to buy.
So I guess the bigger question is, were you looking for high backlash so that you could model it and then demonstrate that, or this is you tackling the problem? If it is the former, success. If it is the latter, I would suspect that spending more money in in better motors results on less study time, which means that you can dedicate your time to other things. I'm just trying to grasp what the goal of it was. If it is to model the backlash, success. If it is to reduce the backlash, I guess it's a design issue.
It's true. It's true. Yes, you're right.
But am I right in saying that you wanted to model the backlash? Is that the goal of part of the work that you did?
Yeah, look, this experiment I did with my pocket money, right, in my home in the pandemic situation. Then
time is free. You're saying time was free, but
yes,
the gearboxes were not. All right.
Yes.
One could argue about the time value of money, but I won't. This is not an economics conversation.
Yeah, sure.
Thank you, Giancarlo. Yeah.
Thank you.
Okay. Any other question? Okay, maybe you will his new harmonic drives. Thank you, everybody. Next,
Thank you.
thank you, Giancarlo. Next presentation is the last presentation of the day. Sofia Larrota will be presenting sorry, I just scheduled. Design of a bionic shape memory alloy fish tail.
Thank you very much.
Please share your screen.
Yes, just want to check if everybody can see my screen right now. Wait.
Yeah, yes.
Right. No. There. So, good afternoon, everyone, and thank you for your attention. I'm going to present the design of a bionic shape memory alloy fishtail, a work carried out by Professor Carlos Francisco Rodriguez and myself. So, the gist of the project is a modular rotational lever mechanism driven by antagonist shape memory alloy wires was designed and characterized experimentally to mimic the behavior of dorsal fish muscles. A multi-body analysis was performed, according to which several of the modules were sized and connected serially to form a bionic fish. Of course, the first relevant question is why we are doing this. So I want to give a small introduction to the context of robots locomotion for underwater exploration. Propeller-based ROVs, or rovers, have been successfully used for open water exploration. However, there is increasing evidence that noise and electromagnetic fields coming from the propeller motors pose significant biological stressors for certain organisms, particularly relevant the shark, which is a species of high biologic interest for many ecosystems. In order to overcome this issue, the use of shape memory alloy, SMA for short, wires, as solid-state actuators, and the use of pisiform propulsion is proposed. Now, for the next session, I'm going to define carangiform locomotion, which is a type of undulatory body-caudal fin swimming mode found in fast-moving fish. It is characterized by high swimming speeds, good maneuverability, and extraordinary mechanical efficiency. The movement is characterized by more pronounced swishing motion near the caudal tail, which decreases steadily towards a relatively rigid body. The gist of the issue is there is no standard technique or model to this day that models carangiform locomotion. And even though the tail flexibility is thought to play an important and yet poorly understood role, fish tails have often been modeled like a series of rigid propulsive elements. So for this study, the fish as a multi-body mechanism was analyzed like a direct kinematics and kinetics problem, in which a piecewise tail with N foils were assumed to have an imposed motion consisting of sinusoidal movements with characteristic amplitudes, frequencies, and phase shifts. Using the principles of D'Alembert's and Lagrange multipliers, we hope to achieve or to analyze and retrieve the joint torques and swimming speeds for a certain swimming configuration of, in this case, 3 plates. Now, for the hydrodynamics of the problem, we concern ourselves with the quasi-steady two-dimensional wing theory suggested by Mason and Burdock in their own Kerangiform robotic fish. According to this model, hydrodynamic lift and drag derived from the Kura-Joukowski theorem is applied to an oscillating flat plate. Now to the system kinematics. We have a vector Q with 3n generalized coordinates. We have a restriction vector, a constraint vector with 2n holonomic pin joint constraints and n drive constraints defined as the relative angle between each segment and the previous one. Given the fact that these two vectors have the same number of elements, we can guarantee the matrix phi sub q is square. Something interesting happens to the mass matrix though, as the fish density is assumed to be roughly equal to that of the surrounding water. In fact, it is necessary in order to achieve neutral buoyancy. So added mass coefficients are considered for the tail segments. The external reactions vector also takes into account that all hydrodynamic forces must be applied to the center of pressure of the foil instead of the center of mass. In this case, it is a quarter point chord of the foils. Now, using this tool programmed into MATLAB, we go on to explain the experimental model of the actuator module. The double lever mechanism was inspired in biological joints in which pairs of antagonical muscles work coordinately in order to produce rotation around the pivots. You can see the constitutive equations of the model. They have 6 parameters, 2 of which are the maximum and minimum elongations of the wire. These parameters were found experimentally. Now, for the single wire characterization, it's important to remember that SMA wires exhibit hysteresis, and we have a contraction speed roughly proportional to the input current, while the relaxation dynamics are grossly determined by the heat transfer due to the surroundings, and thus exhibit a characteristic first-order response. In order to model this, several cooling media were tested and compared. And in this case, propylene glycol was deemed to have a sufficiently fast response and decent voltage current draw. Taking this experimentation, a module was built and tested for fluttering motion at different frequencies. Happily, we can see that the movement is quite consistent, and the actual movement is very closely related. It correlates very strongly with the constitutive equations that were theoretically formulated for this model. Now, using an iterative design process between this mechanism synthesis and the modeling explained previously, we arrived to a the physical configuration of a viable solution, not necessarily the best solution, just one possible viable solution, which contains the three movements of the tail segments for a frequency of 1 Hertz and an approximate swimming speed of 3 centimeters per second. The table includes some rough dimensions for the body segments, as well as some important dimensions for the actuator modules. Given this, you can see a very brief simulation of the chosen parameters, and the very natural movement was achieved, even though The discretization of the tail was not very big. We only have 3 segments. Using this information, we began the actual construction of a prototype made with laser-cut acrylic and 3D printed ABS. A latex membrane was used to encase the tail and isolate the actuators. And this, of course, the body was used to harbor the electronics, and no concerns. This hub was tested first for waterproofing before any live tests were conducted. This is a picture of the finished water fish prototype. And now onto what I think everyone is expecting, the preliminary swimming tests. We can see the activated tail moving in a way that closely resembles a simulation, even though we have some couple of things we need to address. First of all, the prototype is excessively buoyant, and as you can see here from a bag of coins, needed to be anchored to the floor of the tub in order to correctly, well, be able to actually swim, and thus it doesn't yet move. Another interesting observation was that given its nature as a thermic system with a low voltage and high current draw, the energetic efficiency is so far abysmal, which seems to defeat the purpose of mechanical efficiency yet. However, despite these drawbacks, this prototype serves as a successful proof of concept, and extensive further research and testing are required. But I believe the premise is worthy of further investigations. There are many points left to address, but I'd love to discuss your inquiries, thoughts, and ideas on the matter. Thank you for your attention, and I hope you found the presentation interesting.
Thank you very much, Sophia. Nice project. Is there any question for Sophia? Juan?
Sorry, I could not pass asking questions. It seems that that's the standard for me. Great work. If I understand correctly, you started with the premise that what you wanted is to have reduce the impact in the environment, not necessarily the environment as in the natural environment, but the environment the fish are in.
Exactly.
Because you mentioned of having some sort of signals that may affect their behavior. I'm guessing that actual efficiency in the locomotion is not a concern, is it? If the answer is yes, that there is a concern, can you, on paper, in theory, compute or obtain the maximum efficiency that you can potentially have from your shape memory alloy actuators, in that we know for a fact, and you demonstrated that because you were looking for a fluid that will extract the heat the fastest, that most of your actuation power, most of the power that is in your batteries is going to go in heat. So you could, in principle, I suspect, compute what the maximum efficiency would be. And if so, sorry, this is now a series of questions, would that be efficient enough for the use that you're looking for? And I'll stop there. Thank you.
Oh, okay, thank you for your questions. Actually, yes, even though for any machine, I think most engineers would look towards efficiency. However, the main premise of the fish is actually to avoid disturbing the ecosystem. It is interesting to note, yes, absolutely, the system is energetically inefficient, and it would be interesting to make closer estimates of the efficiency it can achieve, especially because it is very easily altered by the temperature of the surrounding water. So one thing, however, that was discussed is this type of actuator could actually be used in environments in which the outside temperature is very high. But yes, I am sure some further investigation and testing would be required. And I think it goes without saying that it maybe becomes a matter of paradox of just because you can does not mean you should. And I'm sure some different alternatives will have to be undertaken, because as is, the prototype consumes so much energy, it is not very viable.
Thank you. Any other question?
No one has one. I have a follow-up, but I'll wait if somebody else has one, so I'll defer to someone else.
No, please continue.
Okay, so if your main premise is not to alter the environment so that you remain unaffected, I can only imagine that a leak of the propylene glycol from your tail is going to have a much more significant effect than any electromagnetic signals that are emitted by a motor. So I suspect that you're going to have to be very, very careful in how this is constructed. I know that it is not really damaging to the environment because glycol, I don't know if propylene glycol is the same, but glycol is used to make ice cream. So it is food safe, but I'm not sure if it will alter the behavior of fish, if that's what you're studying to mimic, right?
Thank you for your concern. And actually, yes, that was one of the main criteria used when selecting the different coolants, was a previous study regarding toxicity in water environments. It's exactly all of the studied coolants were food grade safe and have also been shown to be very safe in delicate water environments.
But the fact that they're safe doesn't mean that if a fish will taste it, will it still behave the same way? That's the premise. So I do understand that they are food safe, but will it alter the behavior of the fish who are, I wouldn't say smell, tasting this as they swimming? Anyway, very interesting. Thank you for the presentation and very well done presentation, I must say.
Rogelio Ecker has another question.
A question regarding the life of the material. I had a chance to make some experiment with antagonic shape memory alloys some years ago, actually many years ago. And I was wondering at that time, what happened with the life, for example, with the fatigue of these materials when they are working in antagonic way. Because when you hit one of them, then immediately you put under traction the one that you already, I don't know if I'm clear on the question. I don't know how to explain it.
Yes, your question is extremely relevant. And that is why, for example, if we see in this module, if this wire contracts faster than this wire can expand, the excessive strain is, of course, going to fatigue the wire. That is why this experiment was conducted in order to find a suitable response time so as not to overstrain the metal. But of course, I did not really analyze this phenomena for an extended period of time, so I could not conclude on on results that could take more time to develop.
Yes, at that time, that was, like I say, many years ago, I saw some works where they used this kind of system, but I couldn't find information on the fatigue for this particular implementation.
Okay.
Yes, no, I couldn't either.
Okay, thank you.
Any other question? So let's thank you, Sophia. Thank you very much. So we close the presentation and the day. Thank you very much to everybody for attending the conference. We are waiting for you tomorrow morning with the plenary speak. The plenary talk by Manfred Justi at 10 p.m. Thank you very much.
Thank you. Bye-bye.
See you tomorrow. I hope you are enjoying this time as more than me. Thank you.
Bye-bye.
Bye-bye.